Swayam Prabha. Digital India. Educated India.
Okay, let's look at the expression for energy again. So energy was P0 times C, which was mc square over the square root of 1 minus u square by c square. This is the exact expression for energy in special relativity. And let's plot this energy of a particle as a function of its speed. Okay, so the speed can only be between 0 and 1. At a speed of 0, the energy is just mc square. Okay, and we can write this as gamma u times mc square, where gamma u is 1 over the square root of 1 minus u square by c square. So if you recall the behavior of gamma as a function of u, it starts at 1 and then it rises, okay, to infinity as u goes to the speed of light. So energy versus u would look something like this. At low speeds, what you would see is that there is a correction to the energy, which is half m times u square. Okay, that is, it behaves like a quadratic function of u for small values of u. But as u gets larger and larger, the energy goes on increasing, okay, till you reach infinite energy when you approach the speed of light. Sorry, when u approaches c. Okay, or in other words, I can go on, if I think of this as the control variable, that is, I can go on pumping up the energy of a particle, but I will never get it to exceed the speed of light. I can only get it asymptotically close to the speed of light by going on increasing its energy. In fact, it would cost an infinite amount of energy to accelerate a massive particle to the speed of light. Okay, so the speed of light becomes an absolute limit for the speed of any particle, because it really requires an infinite amount of energy to get you there. Okay. Now we could ask something else, which is we could look at massless particles. For example, light particles, particles of light, photons. And for these massless particles, okay, this relationship doesn't quite make sense because the mass goes to 0, but the speed of the particle also goes to c. So the numerator and denominator both go to 0 in that limit. So it's not clear what the limit is. However, if we look at the form of energy momentum that we had derived over here, the relationship between energy and momentum takes this form. The limit of this equation is well defined in the limit that the mass goes to 0. So in this limit, what we would get is that the energy of a particle is equal to, so the exact expression is this, and this goes to, in the limit, mass goes to 0. Okay, or energy is P mod P times C for a massless particle. So what we see is even massless particles can carry energy. Okay, they can carry energy by virtue of having a momentum. Okay, in fact, you can, if the particle has 0 energy or 0 momentum, so if it has 0 energy or 0 momentum, such a particle would never really exist. Okay, so to exist, it must always have some small, at least some small finite momentum or finite energy. Okay, so if we look at the exact expressions for energy in terms of velocity, so mc square over the square root of 1 minus u square by c square, we're going to a very peculiar limit where the mass goes to 0 and the speed goes to the speed of light. Okay, and we're saying in that limit, whatever this limit is, there is some energy associated with that. And for momentum, again, we're going to a limit where the mass goes to 0 and the speed goes to 0. And whatever this limit, there's some momentum associated with it. Okay, and the energy of the particle is just related to that momentum times c. Now, what this also tells you is that the only way that a particle of 0 mass can exist is if it's traveling at the speed of light. If it's traveling at any other speed, it would have 0 energy and 0 momentum. Okay, and therefore it would not exist. Okay, so massless particles have to travel at the speed of light. And they carry energy and momentum. Okay, that is, a photon can push things around, okay, by transferring its momentum to something else. Okay, and in fact, you see something amazing here. Okay, it's not that the speed of light is special, it's the speed c which is special. Okay, and photons just happen to travel at the speed c, or this limiting speed of special relativity, because they are massless. And if we were to discover any other massless particles, assuming that the laws of special relativity are right, those particles would also travel at the speed of light, c. Okay, so any massless particles in 2015, we discovered gravitational waves, okay, which are like electromagnetic waves. So they're made up of particles called, hypothetical particles called gravitons. We haven't seen the individual particles, just like before we had discovered individual photons, we knew about electromagnetic waves or light. We've discovered these coherent waves of many photons or many gravitons called gravitational waves. And to the best of our observations, these gravitational waves, which are expected to be carried by massless particles, also travel at the speed of light, c. Okay. So it really does seem like any massless particle, if we were to discover more in the future, would also travel at the speed of light, c. Okay, and the speed is really the thing that is fundamental. It's not light that is fundamental. Okay, and again, just a reminder that this is the speed at which massless particles would travel in a vacuum. Travel at c in a vacuum. Now, let's explore an implication of the equivalence of mass and energy. The fact that mass can be converted to energy means that sometimes we can, in certain subatomic processes, we can get tremendous energy outputs by conversion of mass to energy. So let's look at a particular example. So, of course, you know of particles called electrons, which orbit the nuclei inside atoms. But it was discovered that there are also antiparticles of every particle. So the electron has an antiparticle called a positron, which has exactly the same mass as the electron, but an opposite charge. And now it was also discovered, this was in the first half of the 20th century, that electrons and positrons can annihilate to give you pairs of photons, particles of light. So we could ask now, supposing I take an electron at rest and a positron at rest, so an electron at rest and a positron at rest. So I bring together this matter and antimatter, and I see what the energy of the outgoing photons is. Okay, so I want to know what is the energy of the outgoing photons when an electron and a positron annihilate with each other. So the way we would do this is quite simple. For any process, no matter how many initial particles we have, so let's suppose these are our initial particles and these are our final particles. Now, this is a closed system, right, which is transforming. We're assuming that there's no external energy or force being applied to the system. So what should be true is, from Newton's laws, the sum over 4 momenta of each of these particles, so p mu I, sum over I, d tau, this should be 0 because there's no external force acting on all these particles, which means that the sum over I of momenta, 4 momenta, is conserved. Okay, that is, whatever it is initially is the same as whatever it is finally. So now if we look at this reaction and we write down, so our initial state looks something like this. Our initial state is just an electron and positron at rest, and we're assuming that they're almost or right next to each other so that they can come into contact easily. And so if we write down their initial energies, so p mu, the initial 4 momentum vector, it's E by C, and then we have various momentum components, px, py, pz. This is for each electron separately. And if you'll recall, the energy square was mc square whole square plus p square c square. Now, if the electron and positron are at rest, the velocities are 0, and that means the momenta are 0. So the energy is purely due to rest mass energy, so E is mc square, and px, py, pz are 0. So what this tells us is the energy of the particle by C is mc square for each particle, and if we take both the electron and the positron, the 4 vector sum for both of these will be 2 mc square, because both electron and positron have the same rest mass, by C 0, 0, 0. Okay, and now for the final state, we'll assume that you have 2 photons, and these photons have to be produced back to back. Okay, without loss of, it has to be true, otherwise they would not conserve momentum. Okay, so at least in the reference frame where the electron and positron are at rest. So in what is called the center of momentum frame, that is the frame in which the electron and positron have no net momentum, in that reference frame, the 2 photons that are produced must be produced back to back, because if they're produced at some angle relative to each other, then there will be some direction in which the net momentum is non-zero, and therefore momentum would not be conserved. Okay, so the fact that momentum is conserved implies that the photons have to be produced back to back. And whatever that axis along which the photons are produced without loss of generality, let's take that to be, we'll call that the z-axis. Okay, so now for each photon, we can write down the 4 vector. So let's say for this photon and this photon, it's E by C, px, py, and Pz. Now recall that for a massless particle, the energy is just going to be P times C, or the magnitude of P times C. And Px and Py are 0, so all of the momentum is along the z direction. Okay, and so we can take Pz to be the magnitude of momentum is the same as the z component of momentum, and therefore E will just be mod P times C, and we can write this now, the 4 vector, as E by C, or we can write mod P as E by C. So 0, 0, E by C. Okay, so these are the 4 components of the 4 momentum of photon 1, and for photon 2 it would have exactly the same magnitude of energy and momentum. It would have the same magnitude of momentum. That's easy to see because the momentum must be back to back to conserve momentum. And therefore it would also have the same magnitude of energy because energy is related to the magnitude of momentum. Okay, but in this case, the momentum is along the negative x direction or negative z direction. So now if we add up these 2 components of photon 4 momentum, what we would get is the z component, net z component is 0, okay, as expected because of momentum conservation. And the total energy is 2e, and the component in the 4 vector is 2e by c. Okay, so now what we can do is we can equate the initial 4 vector that we had for the electron plus positron system to the net new 4 vector that we have for the 2 photon system, and we can solve for the value of E. Okay, so if we do that, what we would find is 2mec square, which is the initial energy of the system, is equal to 2e, where E is the energy of each photon. Okay, so the energy of each photon would just be equal to mec square. Okay, so this is now the energy of the photon. It's not the energy of the positrons or electrons. So what has happened is in this process of what is called pair annihilation of electrons and positrons, we have converted the rest mass energy of the electron and positron into kinetic energy of the photons. That is, there is no rest mass energy now in the final state. There is just kinetic energy of these photons. And we can ask, how much kinetic energy do they have? Can we calculate this number? So you would find, if you plug in the mass of the electron, that the energy of each photon would be 0.5 mega electron volts. That is 10 to the 6 electron volts. Now, you could ask, well, how much energy is this in common units like joules? And if I convert this to joules, this would be about 0.8 into 10 to the minus 13 joules. Okay, so this seems like a very, very tiny amount of energy. Okay, and the mass of an electron, if you'll recall, is 9 times 10 to the minus 31 kilograms. Okay, the mass of the electron is very tiny, and the energy released when you convert this rest mass into photon energy or photon kinetic energy is also very tiny. However, there is an important sense of scale which we should keep in mind. So you could ask now, supposing I had a huge collection of electrons. An electron is, after all, a very tiny subatomic particle. But typically, if we're performing a process like this, let's say in bulk at some scale with a large number of particles, then what we would have is we would be converting a macroscopic amount of matter. So let's say we convert 1 gram of electrons. So many electrons. Okay, and this 1 gram of electrons would have of the order of Avogadro's number of electrons. Okay, it would actually be about 1,000 Avogadro's numbers. So something like 10 to the 26 or 10 to the 27 electrons. We would be converting the mass of these into photons. Okay, so the total energy in all the photons that you would produce in the annihilation of 1 gram of electrons and positrons. So per electron and positron, the total energy released in photons would be 1 gram times c square, m times c square. And this m is 10 to the, so in SI units, this is 10 to the minus 3 kilograms. C is 3 times 10 to the 8 meters per second whole square. So if we square this, we would get 10 to the 17, so 10 to the 14 joules of energy, okay, which is a tremendous amount of energy from just 1 gram of electrons. And this amount of energy release is about the total energy consumed by a city over the course of 1 year. A typical city over the course of 1 year consumes this much energy. Okay, so you can imagine what a tremendous amount of energy release this is if you were able to tap in to the rest mass of particles and convert those into energy. It's quite difficult to actually convert rest mass of particles into energy at scale. This happens in typical chain reactions inside fission reactors, where not the total mass, but a part of the mass is converted into kinetic energy or other forms of energy in nuclear reactions, and also in fusion reactions inside the sun. Rest mass energy is converted into kinetic energy, but again, this requires such high temperatures and pressures, and this has not been done in controlled environments on the Earth. Now, we've seen how Newton's laws have to be modified to be consistent with the principle of special relativity. Let's take a look at Maxwell's equations. And since Maxwell's equations actually told us that there is a speed c, which is a fundamental constant of nature, we might expect that Maxwell's equations are actually automatically consistent with the special relativity transformations. So let's see how we can show that. Okay, so let's write down Maxwell's equations. So Maxwell's equations, assuming the presence of a source, can be written in this form. Rho, I'm actually going to use Gaussian units here. So in Gaussian units, I can write this as 4 pi times rho. Del cross E is minus partial B partial t. Del dot B is 0, and del cross B is plus partial E partial t, and the constant c appears over here, and this is plus 4 pi by c times j bar. So rho is the charge density and j bar is the current density. And now if you look at these equations, it's not at all obvious why or how this is consistent with special relativity, apart from the fact that a constant c appears in both these equations, in these equations. Okay, so these are coupled differential equations, and we're trying to solve, assuming we know the sources, we would be trying to solve for the components of the electric and magnetic fields everywhere in space. Okay, so at each point in space, we are trying to solve for Ex, Ey, Ez, and Bx, By, and Bz. So let's count how many equations we have. This is one equation, it's a scalar equation, a 3-scalar equation. This is a vector equation in 3 dimensions, so this is 3 equations. This equation tells us about the absence of magnetic monopoles is 1 equation. And this Faraday's law is another 3 equations. Okay, so the first equation, of course, is Coulomb's law. Then the second one is Lenz's law. And the third is that the statement that there are no magnetic monopoles. And the fourth is Faraday's law. And in total, if we count how many equations we have 8 equations. Now, what you can do is you can define what is called a field strength tensor. Okay, and if we define this field strength tensor, this is a rank 2 contravariant tensor. And if you'll recall, I told you that sometimes we just have to guess what transforms like a tensor. Okay, so if you write down a rank 2 tensor of this form, where I fill in the components of this tensor with the electric and magnetic fields, so I filled in all the entries of this matrix. So what that means is if I take F00, 0, this is 0. If I take F01, that would correspond to this entry, which would be minus Ex by C, and so on. Okay. And the other thing that you'll see about this tensor is it's an anti-symmetric tensor. That is, if I take F nu mu, that is, if I change the indices, so for example, if I calculate F10, this would be the same as minus F01. So F nu mu would be minus F mu nu, okay, in general for the nth and muth components. So this is what we mean by an anti-symmetric tensor. Okay, and by writing the electric and magnetic fields in this tensor notation, we are assigning properties to how the electric and magnetic fields transform under Lorentz transformations. That is, we're assuming that the electromagnetic field F mu nu, or the field strength tensor, transforms like a tensor, which means that if I know the field strength tensor in one reference frame S, and I want to know what the field strength tensor is in a different reference frame S prime, then what I would do is I would calculate, assuming I know the Lorentz transformation matrix, I would calculate something like this: lambda mu rho, lambda nu sigma, F rho sigma. Okay, or in matrix notation, the matrix F prime would be lambda transpose F, would be lambda F lambda transpose in matrix notation. Okay, so if I know the field strength tensor, that is, I know the components of the electric and magnetic fields, and I know the matrices lambda which relate to frame S and S prime, I can get the field strength tensor in the new reference frame. Okay, so this allows me to get the new field strength tensor in frame S prime. And of course, once we have the contravariant field strength tensor, we can also define the covariant field strength tensor, F mu nu, using the matrix G, the metric, to lower and raise indices. So we can define something like this, okay, which gives us the covariant field strength tensor. Which in matrix notation, I can write down the components of this as like so, okay? So this would give me the covariant field strength tensor. Of course, this is not a different object. It's still made up of the same electric and magnetic fields, just written differently. Okay, and if you'll recall, a covariant index transforms using the matrix lambda transpose inverse. And it's also useful to note that in 4 dimensions, there is a particular tensor, which this tensor is useful when we write down Maxwell's equations. So this tensor is called the Levisavita tensor. Okay, and this tensor is defined like so. It's a rank 4 tensor, and it's defined so that epsilon 0, 1, 2, 3 is +1. And if I now exchange any 2 indices, okay, I would pick up an extra minus sign. So for example, epsilon 0, 2, 1, 3 would be the same as epsilon 0, 1, 2, 3 up to a minus sign. So in this case, this would be -1. Okay, and if I make another exchange, so exchange 1 and 3, this would be related to epsilon 0, 2, 1, 3 by a minus sign, or it would be related by 2 exchanges to epsilon 0, 1, 2, 3. So this would just be +1. So in this way, I can figure out all the components of epsilon, mu, nu, rho, sigma. So this is called a fully anti-symmetric rank 4 tensor. So this is the generalization of epsilon ijk in 3 dimensions. This now what we have is a rank 4 anti-symmetric tensor. Now the important thing about this tensor is that if I calculate the components in one reference frame, so frame S, and I know how to transform this into a new reference frame S prime, because this is a rank 4 tensor, so I would have to use 4 lambda matrices to transform it into the Levisavita symbol in the frame S prime. And what I would find is in the frame S prime, the components of the tensor are unchanged. That is, epsilon prime 0, 1, 2, 3 would also be +1, and so on. Okay, all the other symbols, all the other components of this tensor would be exactly the same. So such a tensor where all the components stay the same no matter which frame you calculate it in is called an invariant tensor. That is, the components do not change from one reference frame to another. Now, using this Levisavita symbol, or this Levisavita tensor, we can define a dual field strength tensor. Which is also contravariant. So this is denoted as f twiddle mu nu, which is written as half epsilon mu nu rho sigma f rho sigma. Okay. And in matrix notation, we could work out what this is. And we would get in matrix notation something that looks like this. So you can see that this dual field strength tensor exchanges the locations of electric and magnetic fields inside the tensor. Okay, so our old f mu nu looked like this, and now we exchange the location of minus ex by c. We replace that with minus bx, And everywhere we have Bx, we replace that by Ex by C. Okay, and if we do that, we would get this dual field strength tensor. Sorry, this should be Ez by C. So now that we've defined the field strength tensor and the dual field strength tensor, we can write down Maxwell's equations using these field strength tensors. One more thing that we'll need before we do that is to know how rho and J transform under Lorentz transformations. And you can show that rho by C and Jx, Jy, Jz, these transform like a 4 vector, which I can define as the current 4 vector. Okay, or the charge current 4 vector. So finally, putting all this together, you can show that Maxwell's equations can just be written in this form. So let me write those out here. Partial alpha f alpha beta is j beta, or 4 pi j beta. And partial alpha f twiddle alpha beta is 0. So you get very elegant expressions for Maxwell's equations, and if we count how many equations we have, so this equation has the free index beta. Okay, so beta can take values 0, 1, 2, 3. So this is actually 4 equations. And similarly, this equation has one free index beta, which is also 4 equations. So we get 8 equations. And I'll leave it to you to check that this results in Maxwell's equations, okay, by plugging in the field strength tensors and taking the components explicitly. However, one thing that you can see quite clearly is if beta is equal to 0, then the quantity here has charge density here. So this would give you Coulomb's law. The 0th component of this would give you Coulomb's law. Whereas beta is 1, 2, 3 would involve the current density, so those would give you Faraday's law. And similarly over here, beta is 0 would give you the no magnetic monopoles law. And beta is 1, 2, 3 would give you Lenz's law. Okay, and now by the form in which this is written, we can see that this satisfies our criteria for a physical law, in that the left-hand side of this equation transforms like a 4 vector. There's only one free index beta. And the right-hand side of this equation also transforms like a 4 vector. There's only one free index beta. And similarly, in the second equation, there's only one free index beta for this 4 vector. And on the right-hand side, we're saying that this 4 vector is 0, so it transforms like a 4 vector. Okay, so automatically, just by writing it using the proper 4 vector notation and correctly identifying the components of tensors and vectors, we see that Maxwell's equations preserve the same form under special relativity transformations. Okay, so Maxwell's equations are compatible with the principle of special relativity. And let's write down one more thing, which is one thing that you're familiar with is the Lorentz force law. That is, if I have a charged particle with a mass m and electric charge E, what is the force felt by this particle in the presence of an external electromagnetic field? Okay, and so this would come under Newton's laws. So the force that such a particle would feel would be E. Would be E times the electric field plus V cross B. Okay, so this is what we call the Lorentz force. And in Galilean relativity, we would say that this force produces an acceleration. So this would produce an acceleration of the particle, or a change in momentum, okay, through this equation. So the force would lead to a change in momentum. Now, we can ask, is this law consistent with special relativity? And again, we can write this using tensors and 4 vectors, and we can see, or you can check that you can write this law in the form dp mu d tau is equal to E u alpha f alpha mu. Okay, where u alpha is the velocity 4 vector and f alpha mu is the field strength tensor. Okay, so this would be the Lorentz force law. And you would see that, well, of course, this transforms like a 4 vector. Tau is invariant. Tau is the proper time in the rest frame of this particle. And the right-hand side also transforms like a 4 vector because we've contracted these indices. So there's only one free index mu, and which is a contravariant index. So this also transforms like a 4 vector. And E, we've assumed, is the rest frame charge is a Lorentz invariant quantity. Okay. However, this equation has 4 components rather than 3 components. You can check that for mu is 1, 2, 3, you would recover exactly the Lorentz force law, which we're familiar with in Galilean relativity, except this vector p would be 3 momentum of special relativity, not 3 momentum of the standard 3 momentum that we're familiar with from Newton's laws. Now you could ask, what does the mu is equal to 0 component tell you? And there's already a hint here. Since P0 is the energy of the particle, or E by C, the 0th component would tell you what is the rate of change of energy of the particle with time, or with proper time. And this would be related to the power delivered to the particle. Okay, so this would be equal to the power delivered. Okay, so that's how you interpret the mu is equal to 0 component. Okay, so let's finally write down our summary for today's lecture. So the main thing that we learned today is the character of physical laws. In order for them to be compatible with the laws of special relativity, is that the left-hand side and the right-hand side of any physical law, where if, for example, F is ma or Maxwell's equations, the left-hand side must transform like a tensor of a particular rank, and the right-hand side should also transform as a tensor of the same rank. Okay, so if this is true, then the law will preserve the same form in all inertial reference frames. Okay, so law must preserve the same form in all inertial reference frames. And the only way to do that is if both sides of the law transform as tensors in exactly the same way. Okay. The second thing that we saw is, of course, Newton's laws have to be modified to be compatible with the principle of special relativity. And so you have to write down some generalized force okay, in this way, and this force produces a change in what we call form momentum now. And what we saw is, in the absence, these have to be modified, and in the absence of external forces, it's not mass and momentum that are separately conserved, but some combination of a generalized mass energy, where for a single particle the energy is related to its momentum and mass in this way. Okay, and it's this combination of total energy px, py, and pz that is conserved in the absence of any external forces to a system. Okay, so you get the idea of what is called form momentum conservation. And of course, what this also tells you is mass or rest mass is just a form of energy which is locked up with the particle. Okay, but it can be released in certain specific processes, as we saw with electrons and positrons, which can annihilate to photons. And finally, we saw that Maxwell's equations can be written in a way where the physical law has the nice property that the left-hand side transforms as tensors of a particular rank and the right-hand side transforms as tensors of a particular rank, provided we correctly identify the components of the electromagnetic field strength tensor. Okay, and Maxwell's equations are already compatible with special relativity. However, to make it apparent that they're compatible with special relativity, we just had to rearrange things and write them in the form of tensors. Okay, so writing it in the form of tensors makes the non-obvious fact that electric and magnetic fields must transform in a particular way from one reference frame to another. It makes it obvious how they transform. If you arrange them in a field strength tensor, the transformation of the field strength tensor is obvious. Okay, so this is just like writing the 4-velocity vector has an obvious transformation, but if I just write the components of velocity, those have a complicated transformation. Okay, so writing things as this tensor in this tensor notation is called making Lorentz transformations manifest or apparent. Okay, and once you do this, it becomes very clear when you write down physical laws whether they are consistent with Lorentz transformations or not. Okay, and finally we saw the Lorentz force law is also compatible with the principle of special relativity, provided we switch from identification of 3 momentum to the 3 components of 4 momentum, okay, which are these. Okay, so we need to make this switch, and when we do this, what we find is this. Okay, so the 3 components of this equation are are exactly what you would expect for the Lorentz force law, provided we re-identify the components of the momentum 3 vector. And this also gives an interpretation to what the zeroth component of the modified Newton's laws are. So the zeroth component is related to the change in energy of the particle, which is experiencing the force. And this change in energy should just be, the change in energy per unit time should just be the delivered power.